It's magic time.
Magic time?
I think so. Look at that.
Wow.
Yeah.
Magic time. Woohoo! All right, ready? Welcome, EECS16A. Woo!
Well, not bad, not bad.
First of all, again, I'd like to thank everybody here that coming in class in person. Such a nicer experience, I think.
It's better for them.
Better for you.
See all
better
these
for
empty
us.
spaces? They will be struggling.
Yeah. So, Anna's back.
Hi. Oh, thank you.
That means that now it's going to be way more entertaining.
Way more what?
Entertaining.
Entertaining, yeah.
Yeah.
I'm here for you, Mickey.
Thank you. Okay, so what we're going to do today?
Like this, like that?
No, we did that already.
I missed it?
No, we did it like this, like that last week. You missed it.
Aw,
You missed, but we're
that's
going to
my
do like this, like
favorite
that many
lecture.
times.
What about the game?
The game. Oh, the game. Gaussian elimination game. That's already done. You missed that too.
I'm so good, Sylvina.
You're good at that?
I am.
Well, you should practice. We'll put some practice questions for the staff.
I memorized what a Gaussian is.
Oh, yeah?
Like. Yeah, that's
Okay.
why I can do Gaussian
Cool.
elimination.
Okay, well, what did we do last time? You know, it's already been 2 days, and I already forgotten. So I wrote a slide to remind myself, but also you, because you probably have forgotten as well. That's what happens. So last time we talked about vectors. We talked about matrices. These are these concepts that put numbers in a nice way with some order, either a one-dimensional or a two-dimensional order. And there's a nice thing about those because we can then define additions, multiplications, all that kind of stuff on these type of constructs will then make it much easier for us to write very complicated systems, but also have some really nice analysis of systems as well as signals. And so we're going to continue that concept. And at the end, I kind of just showed you that a matrix vector multiplication can represent a linear set of equations. We can write this really augmented matrix stuff that we did, or just a set of linear equations, in a form that is a matrix vector multiplication equals some vector. And that is a very, very useful way of writing things. In fact, whenever I speak to some of my students, the first thing that we usually write on the board is AX equals B. Why? Because that's what we do. You know, you want to describe a system, and it's a linear one, then that's how you write it, which is magical. Today we're going to talk about new concepts like span, and we're going to do some proofs. Woo, exciting. Proofs is something that students tend to have some difficulty with because it has, some degrees of freedom. It's not necessarily one way of solving it. You have to find a path to reason yourself in a logical set of arguments of, how you go from point A to point B and showing that, B is right. And so we're going to go over that. And maybe we're going to mention linear dependence and independence. Are you ready? I think I'm ready. Are you ready?
I'm ready.
I'm always, yeah. I'm not always ready, but today I'm ready.
You are. Oh,
I am.
That's good.
Oh, by the way, if you noticed the playlist today was Imagine Dragons. Guess who's going to Imagine Dragon concert tonight? Woo! Yes. Shoreline. Woohoo. Super excited. All right. So matrix vector form of system equation. I just mentioned that if you considered this equation, of course I can write an equation, right? Like I've defined multiplication between vectors and matrices and vectors. So I defined this, A times X, and I said, you know what, the result of that, what is the result of A times X? Is it a matrix? Is it a scalar? Is it a vector? What is it? A times X, what is it? X is a vector, A is a matrix. A times X. It's what? It's a vector. The result is a vector. Oh, guess what? I can then take that result of the vector and equate it to some other vector and say, are the elements the same? Right? And when I go and write it down, A times X, this A has lots of interesting stuff. Let me read you the story. Okay, think of it as a book. A11, A12, ... A1n. That's the first paragraph of that story. Second paragraph of the story is A21, A22, ... A2, A2, ... And now that's the vertical ... And then, the last thing. And you do your favorite thing, like this and like that. Woo. And you do the multiplication of like this and like that. And when you do the first paragraph with this like this and like that, then you get really kind of this, it's a scalar, right? At the end of the scalar, right? But that scalar is A11 x1 plus A12 x2 plus ... A1n xn, which is a scalar. And then when I do the like this and like that on the second row, then I get this one, and so on and so forth. And then that should be equal to B1, B2, B3, all the way to M, because I have M of these. And now you look at this, it's like, wait a second. This is constant coefficient times a variable, constant coefficient times another variable. You sum them together, and that should be equal to B1. That sounds like a linear equation to me. What about you? Yeah, it does. And then the second row is a different, because, it's a different story. A21 was a different story, different paragraph. And A22 is different weights, same variables, different weights. So that's a second equation, result in some other value. Whoa, that's a linear set of equations that I can write in this concept of AX equals B. And I can also then, take that, and you remember that augmented matrix that we did? Yeah, I can just write that as an augmented matrix. I take all these coefficients, and I get the result, and I put this with a line, augmented matrix, and now this linear set of equations is described in the augmented matrix form. And what I can do now in order to solve it? Gaussian elimination. Not the game, but the algorithm. That's right. And that will give me the result for this set of equations. So now, when you write small a times x equal b, that means this is a scalar linear equation. Capital A times x vector equals b vector is just a linear set of equations. Just a few of them. And you can find a solution for the vector x that will satisfy, that linear set of equations, right? Those will be x1, x2, x3, all these values. And we just write this. Look, instead of writing all this messy thing, I can just write x equal b. And that's why when we talk about, with my students about MRI, and we talk about a linear system, we write ax equal b. We don't write, oh, you excite those protons, and then you receive those signals, and you turn on these, electromagnets, and you switch them around. That's not, it's ax equal b. Oh, simple. But everybody knows that we're exciting those protons, we're exciting this, and we're receiving some signals out of them. Or if you do tomography, you put X-ray into somebody, and you have some sensor that receives it, right? It's the same concept. Like the physical phenomena is maybe different, but it's the same linear measurement. And then once we put it in this form, maybe we have some good software and algorithm in order to solve them. Okay, extremely powerful. Once you convert that into that type of a problem. Now, once you put numbers in this type of form, we can try to interpret. There's a reason why we put them there. Because it makes it easier to interpret what's actually going on. So what I want to do now is look at different perspectives. Let me try again. Look at different perspective, thank you, of matrix vector multiplication. What does this actually mean in that terms when I have this linear set of equations? So I did my homework, and I color-coded it for you. Okay? I color-coded it for you, and I basically says, how about we look at the row? I mean, we can look in a matrix. There's a row, there's a column, there's diagonals, right? All that kind of good stuff. I want to see what is the row perspective of the matrix vector multiplication that we have here. And so I colored the row. This is orange, and this is yellow. Okay, so you take the orange row. I'm just being silly. Just being silly. This is blue. I know I can see some colors. Not all the colors though. Okay, so this is blue, and I do like this, like that, times this, and then I get B1. That's the first row, right? Like this, like that, and I get B1. Cool, right? So when I'm doing this, I'm going to do kind of like, oh, like this, like that. So let me color blue. So A11 x1 plus A12 x2. Take a look, I'm writing. A13 x3, and then that equals to B1. Isn't that amazing? And then when I do like this, like that on the second, I would get, A21 x1, A22 x plus A22 x3, and A23 x3, B2. And the question is, what does this row mean when I do this matrix vector multiplication? What does it mean? What does it mean? What is B1? B1 could be a measurement, right? Like in the tomography case, B1 was a measurement. So what does it mean doing A11 x1 plus A12 x2 plus A13 x3? How's that gives us good interpretation of what's actually going on? What is really, let's say, x1 is doing? Well, x1, it's here, right? And how does it contribute to B1? X1 is one of our variables that we don't know, right? Like we want to know, okay, is that good variable? Is this a bad variable? Is this a neutral variable? What is it? I mean, like, is it an important variable, not important variable? What is it? Well, if I stare long enough at A11, I'll know kind of how X1 may impact the result of my measurement. For example, A11 equals 0. Do we care about X1 when we do the measurement B1? If A11 is 0, X1 has no effect on the measurement of B1. Useful. A11 equals 1 billion. And the rest are like 0.01. Okay? The rest of the coefficients are 0.01. So what does it mean about X1? Very important, right? If A11 is a billion, it's like 10 to the 9, right? And all the rest are kind of like 0.001, 0.001, 0.001, 0.001, 0.001. Well, really, I only care about X1 in my, because like all the measurements really represent X1, right? Like B1 is just almost X1, just depends on it. So it's useful. That interpretation of rho tells us how each variable contributes to the result of a sensor, okay, of a measurement. Does that make sense? Okay, so that's a good way to think about that. So I can ask you lots of questions about this. For example, let's say A22 is negative, and then so this one is negative, and the rest are positive. What does it mean on B2? What is the information that we have here? What? You don't know? I don't know. Actually, I don't know. I don't know if it's whatever. It's a number. Like it came out a number. But what does it mean having, let's say, A22 being negative and the rest positive? I don't know about importance, but I know that if I have some variable at x1, x3, they're always going to increase. All right, the measurement. Right, the measure is going to be large, and then if it gets smaller, that's probably to knock it down. X2 is the variable that does that. Okay? So it's useful if something affects something in a negative way, reduces in amplitude, some others amplify, right? It's good to know. So looking at the row perspective, it's useful in that sense to understand. Okay? So how each variable affects a particular measurement. Now I'm just going to go like this. When you go like this, it actually looks like a row perspective. But now I'm going to do like this. And when I do like this, when I turn around and I'm going to say, you know what? I looked at the row perspective. Let's look at a column perspective point of view. What do these columns mean in a matrix? Okay? How's that going to be different? Whew, let's think about it. I color coded it for you. Red, orange, yellow. No, blue. I want to say reds and what is this? Green? I don't know. Cyan. What? No, it's blue, cyan. Let's call it cyan. Okay. All right. Blue, red, cyan. And guess what? I didn't color this one. It's just giving you a hint. These are measurements, but I did color x1, x2, x3 based on those columns. And the reason I did it is, hey, what is A11, A21? It's coefficients, right? But it's the coefficient in column 1. But it's like, nicely in a column, so we can call it a vector. We can call it a vector. You want to pick a name? Let's call it A1, vector. Let's just call this column A1. And then let's call this one, second column, A2 and A3. Can I write it that way? All right, this is just different display. Now what am I going to do here? Like this, like that. Let's do like this, like that, because we're going to compute the multiplication. So I'm going to put my hands on it. I'm going to look at my thumb. What does my thumb touch? Does it touch red? Does it touch cyan? My thumb, it's blue, like Berkeley. Thumb. Touches the thumb. Always touches that. Like no matter which row I am, I'm always on the blues, right? And when I go like this, what does my thumb touches? Just blue. Doesn't touch the red. Stanford doesn't go. Right? Thumb. Doesn't touch the cyan. It touches the blue only. So that means that x1 only influences the first column. Right? x1 only influences the first column. What about x2? Second column, the red. And what about cyan? Third column. Okay? So each one of those variables affects only one column. That is super, super useful. And you know what I can say then? I can say x1 multiplies a1, right? Because it goes like this, like that, like this, like that, like this, like that. Always x1 multiplies only a1. So I can write it as x1 multiplies a1. And what about x2 multiplies a2, and x3 multiplies a3, and then we add the result together? That's a different way of thinking about it, right? It's from a column perspective. It results in the same thing. I can just write it this way. I can write the same thing like this, like that, like this, like that, like this, like that, but then write x1 multiplies a1, x2 multiplies a2, x3 multiplies a3, and then you add them. Well, what's the point? What's the point of that? Well, let's just write that. Let's see, first of all, that this actually makes sense. Let's write a1 times x1 times a1. So a1 times x1, there you go. a2 x1, right? That's this, right? That's the blue. And then plus x2 times a2. Okay? Just literally writing it. And x3 times a3. And finally, I get this. So it's the sum of three vectors. What is the sum of three vectors? You sum their corresponding indices, right? Like the same position. So I'm going to go like and kind of write it down, like equal to a1 x1 plus a1 2 x2 plus a1 3 x3, you know, and this. Sum these three will result in this. What is that? That's a scalar. That's a scalar. So I got a 2 by 1 vector, which kind of makes sense because the result of a matrix vector multiplication would be here a vector, which is great. And that should be equal to b1. So really, I got the same result, only thought about it a little bit differently. Right? It's the same thing that I wrote before. Now the colors are different. Before, I had blue here and I had red here. Now I have blue, red, cyan. So the interpretation really, what is x1 doing? In that case, from the column space, like from a column space, what does x1 does? What does the column of the matrix, like the first column, says about the result? What does the first column says about the result? It's what? Impact of x1 on all the measurements. The first column is the impact of x1 on all the measurements. All of them together. And the second column is the impact of x2 on all the measurements. Okay? So, kind of same, but different. It's just a different perspective. You know, you look at a problem, you stare it in the face, and you don't like the face. Right? It just like looks kind of like staring at you, doesn't get it. But then you look from the side, and it's like, oh, what's a nice profile. Right? It gives you a better interpretation of the problem if you can see it from different perspectives. And the row and column perspectives are a useful way of thinking about problems when you try to interpret them. And that's what we're going to get. So what the column means, how a particular variable affects all the measurements. Wow. Okay, so what did we do? Like in the column perspective, what did we do? What did we do here? What did we do? We took the matrix, and then what did we do here? Combined the columns somehow with different weights. What weights depend on? The weights depend on? We add all these vectors, right? We're adding A1 and A2 and A3 together, but with weights. What's the weights? The weights are X, are variables, right? It's a linear combination of vectors with the weights now are variables. Okay? That's what we're doing. So let's talk about what's the definition of a linear combination of vectors in general. Here's the definition. And now I'm going to be mathy. Okay, I'm going to be mathy. Pay attention. Given a set of vectors. What is a set of vectors? Well, you take vectors. You take A1, you take A2, all the way to AM. So how many vectors I'm taking? M. It's a set of M vectors. Okay? You take M vectors and you put them in a squiggly line. Okay, we have M of them. All of these belong to Rn. Okay, they live in Rn. What does that mean? Each one has n number of real valued entries. Okay, that's what this description does. And then we say, oh, we also have coefficients, alpha 1 all the way to alpha m. How many coefficients? We have m coefficients. What type of coefficients are these? They're reals, just constants, right? They're reals. Okay, just scalars, scalars, not constants. And then a linear combination of vector is defined as the following. We take A1, first vector in the set, and we multiply by alpha 1, the first coefficient of this set. And then we add it to A2, that's another vector in the set, times A2, and so on and so forth. And the result of that would be equal to B. Now, what is the definition of equal in a triangle? What is that symbol? What's the definition of that symbol? What's the definition of that symbol? Yeah, but what's its definition? Its definition. That's when you want to write a definition, you write equal and triangle above it. We define it as that. So a linear combination of vectors, B, the results in B, by definition is the sum of weighted vectors. This symbol means definition. That's what it's the definition of a symbol. It's like it's kind of, I use the same word, but like that's how you write definition in math when you define something. Okay? Okay, so that's great. So now we have a linear combination of those vectors. Okay, cool. Now, you want to recall that AX. What is AX? Well, from a column perspective, I'm going to write AX as this, and I'm going to write it then as like that. And then when I do like this, like that, I actually get a linear combination of vectors. This meets these definitions. That definition, right? It's like you have A1 is a vector multiplied by some scalar, A2 vector multiplied by some scalar. So, the result of a matrix vector multiplication is a linear combination of its columns. Very useful when we look about geometry, when we look about, when you want to solve stuff. Extremely useful way of thinking about it. So matrix vector multiplication is a linear combination of the columns of A. That's what you do when you do matrix vector multiplication. Any matrix vector multiplication is a linear combination of the columns. Yeah.
Alpha in the definition and X in the linear combination of the matrix vector multiplication. They're both weights.
This is kind of like the template. Constant times a vector, constant times a vector, constant times a vector. You add them all together, you get a result. That's a linear combination of vectors. This meets the template. X1 is some real number. A1 is some vector. And then you add them together. That's a linear combination by definition. Yeah, these are, in this case, we look at them and we say, yeah, these are weights. In that case, our variables that we don't know, sometimes that we want to solve for, are the weights of the columns of the matrix A. Absolutely. Wow, that's interesting. Let's see how it's useful. Okay, let's go and kind of try to understand. So let's think about a linear set of equation as a linear combination. So let's consider this problem, AX equals B. And this is my matrix A. And this is the unknowns. How many unknowns? 2 unknowns. and then this is the result. Okay? And now I want to solve this. How do I solve this? Gaussian elimination. Not the game, but the algorithm, right? I can do that. I can solve it efficiently using Gaussian elimination. Or I can solve it inefficiently like I'm going to do right now. I'm going to solve it in a pretty bad way from a mathematical point of view, but a good way of visualizing actually what's going on. Okay, so bear with me here. Okay, we're going to solve it in a bad way. Have you ever tried to display a vector on like a grid or something like that? Yeah, have you tried? Yeah, two, at least two. It's possible 3 if you're good in drawing, right? Have you ever tried to represent a matrix, like draw a matrix? It's more difficult, right? How do you draw a matrix? Well, we're going to draw a matrix by looking at drawing its columns. We're going to draw, the matrix is composed out of column vectors. Let's draw those column vectors, right? Let's see what happens. So I have this column that's multiplied by a linear combination, and this is the result, right? That's a vector. So now I can deal with 2 by 1 vectors, right? I can deal with that. Let's do it. I'm going to call this A1, and let me draw A1. A1 is 1, 1, so it's like something's wrong with this pen. There you go. Okay, A1. I drew A1. Now let's draw A2. Let's call this A2. Okay? And let's draw it. What is 1 minus 1? So it's 1 minus 1. It's this point. So there you go. You only need to try harder. If you try harder, you succeed. I tried harder, succeeded. Okay. Oh, wait. So I got these 2 vectors representing this, right? And our unknown variables are going to add them together with some weights, right? Our unknown variables are going to add these to some weights, and we want to find the weights that lead to this result. So let's draw this result. What is this? 3, 1. So it's 3 and 1. There you go. And we call it B. So what, from a geometrical point of view, am I asking you to solve when you solve this Gaussian elimination? I'm asking you, take A1 and kind of expand it to some degree, so multiply it by some coefficient, try to expand it, and then add it some version of A2 such that they end up meeting at the end of this coordinates. That's what it's asking. So how much of A1 I should extend and then add some portion of A2 such that I will reach B. That's what it means. Folks, this is not trivial. Like, it's that interpretation. I mean, I know you're used to solving all sorts of stuff mechanically. This is now an understanding of what is actually being done right now on vectors. And you can think of them as well, from you designing some other complex system. Let's say you want to fly to the moon, and that could be, like you apply motor A, and the motor A could be doing something very sophisticated to your spaceship, so it's going to change your coordinate system in this particular way. It's going to rotate you or something like this, right? All of these can be represented by columns of a matrix. And then you add a few together, and then you see, oh, the spaceship's going to go in the right way as opposed to the other way. If you apply, some value on a wrong vector. Does that make sense? That's exactly what's going on. So now, what I want to do is, I want to expand this, and then add that. It's kind of like, it's really control. Control uses that all the time. So how much of A1 I need to go, plus some A2 to reach B? I'm going to double A1. Okay? Yeah, I'll reach here, and then I'm going to go in B, and I think it's this exact length of B would reach it. Wow, A1 twice, plus 1 times B is A1 twice plus twice A2 would reach B. Okay? So it could be a navigation system. How do I go? 2A1, 1B, got to the result. That's awesome. That's what it is. Okay? So the answer is 2A1 plus 1 times A2. Now I can do the Gaussian elimination. Like row reduction, back substitution, and get the result. Which I'm not going to do right now because, you've done this in the home. You're going to do it in the homework. You've done it in the but this is, it's a 2 by 2. It's pretty easy. And then you get, it's the same. x1 equals 2, x2 equals 1. And that's the result. You get the same thing. So you would get it. But now you understand also what it means from a geometrical point of view. Okay? So reaching something, right? So the question now, I got this matrix, AX equals B. And I'm going to ask you, well, before I gave you a particular B, I'm going to give you now an arbitrary B, some B in R2, some two-dimensional, like 2 values of B. Pick a number. Pick a number. 7. Pick a number. 3. 7, 3. And I'm going to ask you, is there a linear combination of the columns of the matrix A that would reach, what do we say, 3 and 7? 3 and 7. Or if I pick some other value, can I reach any possible B in the plane? Huh? Who says no? Raise your hand. Don't be embarrassed. It's okay. Who says yes? Who doesn't know? It's fair enough. Well, let's see. What I like doing is I think of it as a bread and butter. Okay? So by scaling A1, I can kind of reach any point along this line. Right? Any point along this line if I scale A1. Okay? So I don't like butter. I like Vegemite. You know what's Vegemite? Vegemite is this Australian thing. It's like yeast extract. And it's like sour. It looks like chocolate, but isn't. It's like horrible. It's like really salty. Very good source of vitamin B. But the Australians, they dig it. They just eat it like there's no tomorrow, and I just got used to it. So I love Vegemite. So I can spread all this Vegemite over here. Right? I can reach with my spread every point on this line. Now what does it mean then to add A2? Adding A2 is on every point here, I can just go in the direction of A2. Right? And add it. Right? So if I reach this point, I can now go anywhere I want on A2. Because I can add some fraction of A2 to it. And if I ended up here, I can add A2. So I can effectively take a knife now and spread that Vegemite throughout my piece of toast. Okay? And reach everything. And just for you to understand this, I've prepared a video for you just showing this exactly. So that is a piece of cracker. Take Vegemite. It's a yeast extract. Very good source of vitamin B. You open it. It's great. What are you talking about? You take a spreading knife, and then you spread it nicely on that piece of cracker. Oh, look at how yummy it is. Spread it exactly along A1. Because these are all the points that we can reach with A1. Look at that. Oh my God. That's great. Okay, so now it's spread over A1. And now I want to reach, can I reach every point on that toast? Or in that cracker? Absolutely. I'm going to smear it in one direction. Can go in another direction. Now it's all fully covered and ready to eat. And then you just go and eat it. Ah, it's amazing. Here's a different interpretation. No, seriously. Let's say I've got one vector which is in this direction. Okay? Let's say this is the x-axis, right? And I'm going in this direction. So now I can pretty much go anywhere I want. Now the question is, can I now hit every single student here with a stick? That's really the question. So let's see. Raise your hand somewhere here. Oh, you want to be hit? Not a problem. So I travel along this axis, and then now I've got A2 here. And I'm going to extend A2. Oh, don't worry, it's pretty long. And then okay, so I can hit the student. Thank you. But that wasn't a challenge. Come on, challenge me. Ooh, there you go. What about that student? So I have to travel a little bit more along A1. You think you're challenging me?
Let me know if you need help, Mickey.
I might.
I'll give him support.
Yeah. You hold this.
Yes, I'm gonna hold it.
Demo's hurt.
Oh.
Hold on.
Got
Anyway, so you got the point. I can reach every point with these two vectors that are, in this particular, were orthogonal to each other, right? Thank you. Okay, so that's great. Now here's the question. What about this matrix? 1, 1, minus 1, 1. Can I now reach every student in that plane? Well, I can go anywhere I want. Like I could put my Vegemite. You know, Marmite is also another product which is more like British, but it's not as good. Vegemite is the best. And then you go anywhere you want here. And then you want to go in a direction of A2. What is the direction of A2? It's the same direction. So, like, it's not going to help me. I'm just always going to be stuck on this line. Right? Back and forth, back and forth. Yeah.
So can you reach any point as long as the two lines are narrow?
As long as the two do not actually, as long as those two do not exactly be on the same direction, yeah, I would be able to reach anything, right? I'll demo that for you, actually. Okay, so this is not, unless it's along, this line, right? So what about 1, 1 and 1, 0? What is 1, 1 and 1, 0? Hold on. It's this one and 1, 0, right? So one is along the axis, and then the other one is not along the axes, right? So let's now say that this is the axis, right? And now my other vector can grow only in this direction.
I'm holding for you.
Thank you. So come on, raise your hand. Let's do you, okay? So you're that long. I'll need to travel a little bit along A2 here, right?
I'll follow you.
And
I can see.
I'm going to travel along A2. This is still in the same direction. And, whoa, I'm extending. I'm going to fish you. We should use it for the microphone. Raise it. And, oh, wait. I'm going to poke your eyes. Hold on. Close your eyes. Thank you. What's the score of the game? 1-0. To whom? Real? Manchester United. Okay, cool. We pay attention. Real against Manchester United.
No, Valencia.
Valencia?
Okay. Oh, it was Real Madrid.
Real Madrid, yeah.
Okay. Yeah.
Who's winning?
Manchester.
Real Madrid
Real
is
Madrid.
winning. Okay, so we were able to reach. So you could see how I can reach every point in the space, right? So that is still true. I can reach any point. That's cool. Wow, that's nice. So now I want to talk about what does it mean to have, this ability to reach anything. Sometimes we call it a span. The spans of columns of a matrix. That's everywhere that I can reach. Okay? The space that I can reach. It's also called the range of a matrix. It's also called the column space of a matrix. It's just gonna use all those terminologies: span, column space, range of a matrix. All these things are similar. Okay, they're the same concept, but pretty much what linear combination of the columns of A that I can reach some other vector. Okay? So here's the definition. Okay? When you say a span, can you say the span of A? Well, if you say span of A, I got text messages. When you say a span of A, then
You can do Chewbacca.
well, it doesn't work.
Hmm.
Or I think I'm connected to my thing.
Oh, you're connected to the.
Don't say span of A. Just say the span of the columns of A, okay? Or the span of the rows of A, but never say span of A. Span of A means nothing, okay? So the span of the columns of A, or the column space, or the range of A, that's okay. Range of A is okay. Column space of A is okay. Span of the columns of A is the set of all vectors B such that AX equals B has a solution. Not always we can have any B possible. Sometimes we won't have a solution. You saw that when we did Gaussian elimination. Sometimes we had infinite solutions. Sometimes we had one solution. And sometimes we had no solution. So the span of the columns of A is the set of all vectors such that AX will be has a solution. That means all the vectors that can be reached by all possible linear combinations of the columns of A. So in the first case, when I went with a schmear, with a thing, or when I went here around and I hit like two students over there, I was able to reach any of you. Second case, when the vectors were oriented in the same direction, I couldn't. In the third case, I was able to, right, with the help of Anna, because I could barely lift this anymore.
It was too impressive.
Thank you. So here's an example. Okay? Here's a matrix. And the question is, what is the span of the columns of A? R2, entire R2. Everywhere in space, in this two-dimensional space, I can reach because I can go and do this spreading or whatever. Okay? And the way I'm going to write it in a mathy way, which is important because it's a language, the span of the columns of A. Don't write span of A. We're going to cry. Spans of the columns of A is, what is it? It's a set. All vectors V such that V is a linear combination, alpha times 1, 1, plus beta times 1 minus 1, where alpha and beta are real values. That's the same thing as saying this or this. It's the same thing. All the vectors V, all the set, okay, of all vectors that can be reached by all possible linear combination of the columns of A. Alpha and beta are the coefficients of that linear combination. This is the first column, this is the second column. I can do now and say, oh, what is the span of the columns of this matrix? And I would say, oh, the span of this is all the set of vectors V that are just a linear linear scaling of 1, 1. Now you can say, oh, why not just add beta minus 1 minus 1? Which would be actually right. But it's redundant. Because I can already reach minus 1 minus 1 by multiplying 1, 1 by negative 1. So it's just no point of writing it. Yeah. The range of the matrix. The range of the matrix is the same. Column space is the same. We're going to talk about subspaces and spaces. We haven't talked about that yet. So that is the span. And so the answer here is that it's the line x1, x2, x1 equals x2. That is the span of the columns of A. This line that satisfies x1 equals x1 equals x2, that is the span of the matrix. So this one-dimensional line is the span of the columns of the matrix A. Does that make sense? That's a mathy way of writing the same thing. That's a graphical way of writing the same thing. And in words, the span of the columns of A. Okay. Let's do a definition. If reverse E, what is reverse E? It's a mathy way of saying there exists. Okay? It's a mathy way of saying there exists. If there exists a vector x such that ax equals b, okay, so we have ax equal b, and I'm asking if there is some vector x that satisfies that, then b must be in the span of the columns of A. If there is solution, if there is x that satisfies this, means that there is a solution, then this vector b is within the span of the columns of A. That's cool. Right? Oh, yeah.
So that means that B has to be like linear combination of the columns.
Yeah. That means that B has to be a linear combination of the columns. And here's, yeah? Well, we're going to talk about it, in a second when that maybe isn't true. Actually, let's just go back here. And let's say the vector B is this. Oh, let me pick the different color. This is the vector B. Is that true? Can B be reached by a linear combination of A1 and A2? No. What about B being here? Yeah, because that's on the line, right? So then if B was there, then what's solution? If B is here, then there's no solution. Which actually leads to kind of my question, what if B isn't in the span? Thank you for that. That means that there is no solution for Ax equal B. That's the case when you solve Gaussian elimination in the tomography case and we saw their inconsistent set of equations. Right? Like we couldn't solve it. That means that B is not within the span of the columns of A. Let's do this quickly. Ready? Here's the problem. Come on, get your phones. Do it, do it, do it. What are the values of this matrix ABC such that the span of the columns of A are in R3? Span of the columns of A in R3. Okay, everybody took. I'm going to do a response thing. Twenty more seconds. 20, 19. $15. Don't talk. Just do it. Do it yourself. 5, 4, 3, 2, 1. And this is the result. Okay. 47% of you says all the above. Second one is A not 0, B not 0, and C not 0. Okay? All right. I'm going to erase this and now discuss. Okay, discuss between you, argue. Fight. Okay, take a picture and fill your results. 20 seconds. Ready? Oh, you're not filled. Come on, do it. 116. Come on. You could do it. There's only 150 of you. 169. Okay, there you go. Oh, okay. Now 75 say before it was 49, now 75% say all the above. Let's look at the result. Actually, let's look at the question. So the question was, what are the values of A, B, and C such that you can reach anywhere in R3? Now let's say C is 0. C0 means that I don't have the ability to go in one direction. Like any linear combination would keep me in the plane. If C0, any linear combination of the columns will keep me in the plane. Now let's say I want to replace the lamp. Can I reach the lamp? What is the condition to reach the lamp? C has to be a little bit non-zero, right? Because let's say now C is just tiny bit, like a small one. Then I can just go and extend it. And then if this is the lamp, I can just go backwards and stuff and eventually reach the lamp and turn it off. Okay? So it's enough that I have a small component in C then I could reach anywhere in R3. Hence, it's all of the above. Why? Because any solution, all the solutions that I provided you had some component in C, except, one of them says, oh, except C not equals 0, which is a good thing. Okay, does that make sense? Yeah.
Isn't there only like 2 variables? How are you going to 3 dimensions with only like 2?
There's 3 variables. Okay? Otherwise, if it's 2 variables, what happens when I do AX 3 by 3 times 2 by 1? I'm just going to cry. I'm going to cry. I want to move on. If you want to ask a question. Okay, what I want to do now in the next 20 minutes is do some proofs. And proofs are something that people are having I'm going to take questions afterwards, unless this is like super critical. Okay? And then you can just come over after, right? But there is a methodology of how to do proofs. People develop. Actually, one of the things that are amazing in math is that people come with certain constructions that can prove certain things. And then once they've come up with a new construction, people adopt that and use it to prove new theorems in new different ways. So that's an exciting thing in math. Now, the thing is, the thing about truthiness? You know what truthiness is? It's truth that comes from the gut. That you have this gut feeling that's true. And a lot of people are wrong when they have truthiness. They go, that must be true because, I don't know, if they sell on Facebook. I feel it. Feel it in the gut. I know it's true. The beauty about math is that it can be absolutely true. You can have an hypothesis and you have conjecture, but if you prove it, it's true. Not from the gut, it's actually true. And that's the beauty about proofs. So how do you go about it? First of all, what you want to do is you kind of write the direction of the proof. Like if something, something, then something, something. That'll be kind of the theorem that you want to prove. And then you go like, well, I can now go and derive it for Rn, but that's difficult. Maybe I'm going to start with R2. Or maybe I'm just start with just constant variables or something that's easy for me to go and find kind of the pattern that I want to do. Okay? So you're going to start with simple to see some pattern. Then you want to use what it is known and also definitions of other theorems. So you know something in, like if da-da-da-da-da, so there is something that's known there, then something. So you're going to use what it's known in other theorems. And then you're going to manipulate both sides of the argument and justify every step that you're going to be doing. Is it important? You cannot just do steps without justifying them. And then eventually reach, for example, that they're similar, the same, or they're different. And there's different type of proof. One of them is a construction, like constructive. You try and go and build, and then you get the result. Or you can say, let's prove by contradiction. For example, Mickey is always right. How do you go and prove that?
Give one example where you're wrong.
One example when I'm wrong. If I was one time wrong, then obviously this conjecture is not true. Okay? Sometimes it's just easier. Let's say I prove that. Okay, we'll get to that. Okay. It's easy, but I just couldn't think of an example. We're going to do now a constructive one. Remember we talked about Gaussian eliminations, and I said, you can do Gaussian elimination using 3 basic operations that don't change the solution. And I said, multiply an equation with non-zero scalar would not change. And then you believe me, and then we're like, Gaussian elimination, not the game, but I did that, but you've been solving it. We didn't prove this. Let's prove it. Let's prove that this is true, that we can actually do this. Okay? And really what it says is that 2x plus 3y equals 4 has the same solution as 4x plus 6y equals 8, for example. I multiply the equation by 2. Okay? So I multiply the equation by a non-zero scalar, I get this, and I'm saying the solution for this one, x and y, is the same as the solution for this one. Okay, let's prove it. So what's the direction? Are we going to prove it for Rn? No, let's prove it for R2. Why? It's simple. Okay, it's much easier than now doing all these infinite sums and all that kind of stuff. Let's just prove it for n equal 2. So there is some direction that I want to do, right? So I want to prove that the solution for one is the same as the solution for the other. How do you even go about it?
Maybe define a material linear system
Okay.
or a scalar.
Okay. And
And then,
does one has that has a solution?
right.
And let's just pick a solution for that system. Let's start with that one, and then multiply, and then see that it's the same. Okay. Here's an idea for a proof. Okay. Let's start with some arbitrary linear combination. Ax plus by equals c. Okay. A is constant. I mean, it could be 3 or something, but it's parameterized. Like, it doesn't change. A doesn't change. B doesn't change. C doesn't change. These are representing some numbers that are explicit. Now, for each one of those, there will be some x and y that will give a solution, if there is a solution. What will be those x and y's for this parameterization of A, B, and C? Well, we have to pick an explicit one. The explicit ones are x0 and y0. Okay, when I write this, it could be any x, it could be any y. Now I've chosen the numbers. I'm telling you some x0 and some y0 is the solution for this particular A, B, and C. Okay? This is a small conceptual thing, but you can think about it as A being 1 and B being 2 and C equals 3, and now you've got specific x0, which is, I don't know, -1, and specific y0, which is like plus 30, I don't know, whatever. That satisfies that. Yeah, I said something wrong completely now, which obviously proves what you just said before, that I am wrong sometimes. But the concept is the same, that I wanted to say that these are explicit solutions for this equation. So now we know that we have a solution. Okay, so what do we do then? Is say, oh, if this is a solution for here, what does it mean? This is the equation, this is a solution. What does it mean? Can I write mathematically, what does that mean? This I said in words. What's in math? The what? Oh yeah, you do this. You know what's this? Substitution. You substitute those variables. You put them explicit solution, right? So I can go and write, thank you. Ax0 plus by0 equals c. That's what I know. That's what it means to have explicit solution. Okay, this is true. This is true because that's what we said. That is known. What we don't know, what do we need to show? What do we need to show? If we multiply a constant to that set, it still has the same solution, right? So if I multiply ax plus by by some constant and c by some constant, then the solution x0 and y0 is also the solution for that. I can write it in a mathematical way. I can write it as beta ax plus beta by equals beta c. And saying, you know what, the solution for this one has to be x0 and y0. Now, I don't know that. I need to show that. If I show that, I'm almost done. I'll tell you why I'm almost done. Okay, let's show that it has the same solution. How do we go about it? That's right. Substitute. That was nice. Like I substituted, I got a solution. Let's see if it's true. Let's manipulate stuff on both sides. Let's substitute x0 and y0. Now I'm going to substitute. So substitute x0 for x and y, and I get beta a x0 plus beta b y0 equals beta c. Now, I don't know if that's true. I need to show that that's true. How do I show that that's true? Can I divide by beta? That's one way. That's one way. I can divide by beta. That's true. Let me just actually do something a little bit different. But yeah, if I divide by beta, then I need to
Mickey,
use this, which I could.
so we already said before that C is equal to AX sub 0 plus B Y sub 0, so you can just substitute that in for C, and then, oh, actually, never mind.
Yeah, I'm not sure I follow, but just for the brevity of time, let me just go and, can I do that without any assumptions? I can do that, right, without any assumption. I'll just take this as a common multiplier, and then I have this, right? What I can do now, what is this? That's C, right? That is C. So, substitute C. Is that true? Is beta C equal beta C? Yeah. Nice, right? So I proved that if I have an explicit solution, I multiply by beta, it's the same solution. What I have not proven that that solution is unique. Maybe by multiplying by beta, maybe I created a new solution. For example, if I multiplied by beta equals 0, then anything would satisfy that, which kind of what you've alluded to. Right? So we need to maybe show the other way. One way to prove it is to go the other way. Let's say now, does that make sense? Like maybe I created, like obviously you think it's like, no, I didn't create a new solution. But if beta was 0, then I definitely could have created new solutions, right? But maybe there's some other thing that I haven't thought about. Let's try to prove the other way. Let's start with the other way where it says, you know, let's start with beta ax plus beta by plus equals beta c. That has one solution. Okay? Let's say y1 and x1 are solutions for the beta times. What I want to show now in the reverse is that x1 and y1 is also a solution for ax plus by equals c. If I go backwards, then it goes both ways. There is just one. I didn't create new solutions, and that is always true. Okay? So that's what I know. Now I want to show that ax plus by equals c has the same solution. This one. What do I do? You have that? Now, you know that beta is not 0. How do we know that it's not 0? It's part of the statement of the theorem. Right? Multiply equation with a non-zero scalar. Beta is not equal 0. Now I can divide by beta. Since beta is not equal 0, then I can divide and say, oh yes, ax1 plus by1 equals c. So it's the same solution. And now I can do KQED 88.5 megahertz. Ta-da! Oh, it's QED. It's not KQED. KQED is a radio station. QED. Okay? So now I proved this theorem. Now we can use it. Guess what? That's not the only theorem that we need. There's another one. adding a scalar constant multiple of one equation to another. Right? We use this also. And now the question, how do you go about improving that? And let me argue then, if you use the same idea of finding an explicit solution, setting an explicit solution, substituting it, showing that solution's still the same, that's the way to prove. You can try to do the exercise yourself. You can look at the notes. But I really recommend going through this process yourself. It would be a really good practice of learning how to prove stuff. And then there you will also need to show the reverse, but in the same way that I did this one. Okay. So, span of the columns of A is a set of all vectors B such that AX B equals solution. That is the definition. But I didn't prove it. I showed you using kind of like simple things. I showed you that this is true, but I didn't prove it. I'm going to prove it next time. I'm going to give you an idea of the proof. And the proof, right, one of the examples I told you is like, oh yeah, 1, 1, 1 minus 1 is spanning R2. I told you, but we didn't show it. How do we go about and prove it? What I'm going to do is I'm going to use what I know, that a span is a linear combination of vectors. So if I take these two linear vectors, I can reach any point on R2. How do I do that? I pick an explicit solution, some B0. And I'm going to show you that I can find the linear combination for that B0. If I can find the linear combination for B0, then I can reach any point. That is the concept of the truth, of the proof we're going to show next time. And we're going to use, guess what? What we just proved this second ago, Gauss elimination. That's what we're going to use in order to prove this one. Okay? Proof upon proof upon proof. And we build a good house of concrete. See you on Tuesday.
I have a quick question with the spawn. So what is spawn is like?
Span is all, I mean, there's a definition, right?
On top, yeah, on this line.
So the span of the columns of A is the set, all the vectors B, that AX equals B has a solution. That's what definition.
So the spawn is just showing that like there's a solution to to vector A and A1 and A2.
If you do a linear combination of A1 and A2, okay, then basically it's the space that you can reach.
Yes.
In this case, combination of A and A2, A1 and A2 would reach any point.
Yeah.
So the span in this case is R2. But here the span is just this line.
Yes. So how do we write?